This video is meant to be a review of the core concepts involved in doing our calculations involving acidity or basicity. So we're going to talk about pH, pOH, we're going to talk about equilibria involving acids and bases, how it relates to the auto dissociation constant of water, Kw, and also just remind us of some of the other factors that are going in, and some of our jargon and terminology. Now I want to remind us that pH equals the negative log of the concentration of H plus ion. This could also be just written as H3O plus. Make sure that you're keeping it consistent with whatever notation you're using to write your balanced chemical equation though. And you've seen in other places that if we have it written as H3O plus, things still work out. And if we have it written as H plus, things still work out as long as we stay with one or the other. And when we're talking about an acid, we typically want to set things up in this sort of a format. Now, I'm going to use acetic acid and the acetate ion, which I'm going to shorthand as AC for the acetate ion. I'm going to use that as kind of our exemplar case of a weak acid in this. So we're going to have the equilibrium of acetic acid into H plus and AC minus. And we could have had that written as H3O plus right here. We'd have H2O over here. And like I said a moment ago, notice that we get the exact same form for our K value because the water would drop out since it's purely liquid. And so it appears as 1 in our equilibrium constant. So this is going to be the equation as we'd write it for the Ka value. We can also consider the opposite side of all of these things. We can be thinking of things as a base. For that we want to be talking about pOH, which is going to be the negative log of OH. That's what the P is telling us. And we can have this be the case for anything else. We could have this be P of silver ion. I'll go ahead and I'll put that up there just to remind us of the math of it. This would be negative log of OH minus. And in my extension example below, that'd be the negative log of silver ion, or whatever else we wanted in there. So just remind us of what the P was actually telling us. Now when we have it written as pOH, we want to be focusing on the reaction as being the basic side. So we want to be looking at the conjugate base of the acetic acid, which would be AC minus, the acetate ion. Notice if we write that with water, it will yield acetic acid again. Oops, whoa, that was silly. Plus OH minus. Now for that we're going to call that a Kb constant. Now some people, they see the OH minus here and they say, wait a minute, that's pretty weird. I just can't picture making a strong base and calling that an equilibrium. Well, remember, we didn't have a problem with it when we were talking about making a strong acid, because it's not really making a strong acid or making a strong base. We're just saying we're making this ion. And this ion can react with things in solution, and it can exist in equilibrium. So I just thought I'd head off that bit of confusion that some people have. Now, also let's consider what's happening in our water. Water can autoionize, or autodissociate, however you want to think of that, into H plus and OH minus. We have an equilibrium constant for that we have pretty well memorized, and we say that that's going to be 1 times 10 to the negative 14. Now if we take the negative log of that, anytime we take the negative log, we put a p in front of it. So pKw, negative log of this would equal 14. And notice I've kind of left off any sig figs. In fact, I have 0 sig figs in here because I've just taken a negative log, and whole numbers don't count as significant on that. They're just placeholders for where the decimal point was. Now all of that's intentional, and here's where I wanted us to see something. What I'm showing here is the NIST's list of pKWs over lots of pressures and temperatures. Now, this is the temperature and pressure that we're typically talking about 25 degrees Celsius. And for that, our equilibrium constant will be 14. But as we add higher temperature or higher pressure, we're going to see that Kw decreases pretty significantly. So make sure that you're aware of that. But most of the time we're going to be staying with the definition that pKw is 14 and that we're staying at our typical pressure and temperature. So let's remember something important about Kw as well. So Kw equals Ka times Kb. So this number has to equal these two things multiplied together. Now an important consequence of that is that our pKa plus pKb has to equal pKw. In other words, add those together, they have to add up to 14. So you can see we have a number of ways of getting between Ka, Kw, Kb, and any of our p versions of those two numbers. Now the rest of what I wanted to remind us of was the idea of a weak acid and a weak base. Remember that weak acids and weak bases will always be conjugates of each other, and they will be in equilibrium with each other, so the acid form and the base form. That's a really long equilibrium arrow. Now, I was also using that as a divider from what was above. Now you can see here that for the weak acid form, we're going to be writing our Ka. Now if we're writing it like this, let me go ahead and just shorten it. Let me just do Ha form, so the proton-on form will be in equilibrium with H plus and A minus. So Ka, using the same rules we have for any equilibrium constant, will be my products and over my reactant. And of course water can be drawn in that expression. We could have had that written as Ha plus H2O liquid. And of course the liquid doesn't end up appearing in our equilibrium constant. Then we have to make sure that we do our balanced equation with H3O plus and A minus. These forms are completely interchangeable. We can use them however we'd like, but let me caution you, especially if you're going to have to worry about systematic treatment of equilibrium later, especially then, make absolutely certain you stay in the same family of equations throughout. In other words, if you're using H3O plus, don't suddenly switch to H plus, and vice versa, because you're going to end up getting yourself painted into a corner as you're going through your systematic treatment. You're going to have to do some clever things, but of course as we get clever, we also sometimes get sloppy, and that's the easy time to have something break on you. Now, remember also what our Ka means. If it's a small value, that means that we're going to have things stay attached, because for small values, most things are going to be staying attached together. Remember, big number in the bottom, small number on the top means small fraction. And so things are going to be primarily staying associated. So you'll have it small, that's going to stay together. Large equilibrium constants, now we're saying that we have small number on the bottom, big numbers on the top, so that's going to be broken. So that's when you actually have the ions break apart. Okay, and I'll just remind us that hydrofluoric acid acts as a weak acid, so it will have a Ka, and I'm just going to say that there's a very complicated, detailed explanation that you can find out there, but almost any explanation you read that gives it to you in one paragraph or less is really doing a lot of hand waving, almost to the point of lying. But we know that the outcome is the same. We know that it's a complicated scenario, so we live with it. Now the last thing I want to point out, though, with equilibrium, remember what we're saying is that particle A and particle B are going to encounter each other and stick together. And sometimes they're going to stay stuck together, and sometimes they're going to pop back apart. Now what if we end up in what's called the infinite dilution case, where we don't even have this one, all we have is this one ion and this one ion, and we give them as much room to move as they'd like. Well, keep in mind, they're going to do their random walk. They're going to just start kind of going wherever, and in net they may end up drifting in a particular direction, but it's a totally random thing. This one may or may not go in that same direction. But the biggest impact is this doesn't encounter this for a very long time. Once it does, it's going to stick for a moment, pop back apart, start drifting away, and they're just not going to find each other. The reason that things end up acting as weak acids is because they find a partner to exchange with all the time, like the one we had drawn over here originally. So if you go toward infinite dilution, where you're down to one molecule or one pair of ions dissolved in very large volumes, then effectively it's going to be pulling your equilibrium completely dissociated. And so Ka will be massive whenever you're infinite dilution. As you get to realistic working conditions, you're going to have less of that. Okay, so that's the end of the review that I wanted us to have for these core concepts. If there's anything there that's uncertain or a little uneasy in your mind,